ferromagnetic. So out of these 3D elements, only these 3 are ferromagnetic under normal conditions. Towards the end of the last lecture, we came up with the energy associated with the Hubbard model. And the Hubbard model takes into account the Coulombic repulsion or the interaction between electrons. And this energy was given as for the total volume of the material V over small v. Capital V is the volume of the material, small v is the volume of the unit cell, U over 4, U is the Coulombic repulsion factor, the site occupancy is X, minus N V over mu V squared. So we figured out that if the material were to become magnetized, which means M goes up, then the energy associated with the repulsion between the electrons goes down. The collective energy of the electrons is going to go down. But when the material becomes magnetized, the spins tend to align themselves. This is what happens in a ferromagnet. And when they tend to align themselves inside the band, if I make a simplistic picture of a band, this is the energy axis, you occupy higher and higher K levels inside the band. Because if the spins are to be parallel, they must have different values of K. Otherwise, Pauli exclusion principle is not going to be satisfied. So this magnetization drops the energy, but then that increases the kinetic energy of the electrons. So a certain compromise has to be achieved. There is a competition between these two kinds of interactions. So Stoner proposed the Stoner model, which actually comes up or proposes a criterion with the help of which certain materials can become spontaneously magnetized, which means they could become ferromagnetic, even in the absence of an external field. So if you look at my lecture number 12, we discussed the concept of polyparamagnetism, in which I have the energy on this axis, the density of states I have here, and if I assume a nice model for the band in which the band is represented by a parabolic curve, then for this particular model I have a certain Fermi level, and I split the bands into two spin split bands, two spin sub-bands. One is spin in one direction and the other represents spin in the other direction. And up to the Fermi level, both of these bands are equally filled. So the sample is unmagnetized in the absence of an external field. So this is the condition when V equals 0. Now what we could do is we could apply a magnetic field. The energy of this spin, which is parallel to the field, might go down. So this band shifts downwards, and the energy of this spin, which is in the wrong direction, goes up. So this band shifts upwards. Now the Fermi level doesn't shift up to first order, and the number of spins that are up is higher than the number of spins that are down. So this net polarization difference creates magnetization, and this is called polyparamagnetism of these free electrons, these conduction electrons. Okay? But this requires the presence of an external magnetic field. The splitting between these levels is of course 2 mu BV. And we also calculated the polyparamagnetism as N mu naught mu B squared. Alright? So this is something we've already seen. But certain materials are spontaneously magnetized, which means they are ferromagnetic. So you don't need to apply an external field. And you get a difference in the spin up and spin down polarizations. Whenever there is a polarization, which means n alpha minus n beta is not equal to 0, you will get some magnetization. The magnetization, of course, is this factor. If I look at spin half electrons only, this is what the magnetization of a material is. So there has to be some polarization difference for a material to have some magnetization. Now let's look at the concept of a ferromagnet, which is derived from the Stoner's model. And let's try to see how this competition between the Hubbard energy and the kinetic energy can actually favor the spontaneous creation of magnetization in certain cases. So now what we would like to do is we would like to talk about the Stoner model in a hope to explain ferromagnetism. Suppose I draw this picture again of the spin split band. This is GE, this is my E. Once again I draw these nice simplistic bands. This is my Fermi energy, EF. This is the majority spin, the minority spin. Under normal circumstances in the unmagnetized space, both of these volumes are the same, which means the sample is unmagnetized. Now suppose I do the following. I pick up a small number of electrons from this band and place them here. They have to go here because this band is completely filled. They can also go here because these spins are opposite. But if this band is completely filled, since I've done the spin splitting here, which means this band is completely filled and this band is completely filled. I've drawn this band in such a way that this is a completely filled band and this is a completely filled band. The band really is like this, isn't it? It's just one band with spin up and spin down electrons. If this is completely filled, it means that if I split this band into two conceptual spin split bands, both of them will be completely filled. So this volume of electrons can only go here. It cannot spill over into this band below the Fermi level. It has to go to above the Fermi level. So what I'm trying to do is I'm trying to raise the energy of these electrons by some amount, and they are deposited here. Suppose this is a small energy delta E. The density of states at the Fermi level is denoted as G at EF. So when this number of electrons goes here, there is an increase in the kinetic energy of electrons. And the number of electrons is now different for the majority spin and the minority spin, because you have more spins of this kind now. Okay, so now what we're doing is we're flipping these, reversing these spins and increasing their energy. Their spins must flip in order to go into this band. So we are flipping the spins of these bands that are at the Fermi level, and since nearby levels are available, so this kind of interaction can take place. So the energy of the system is going up. You see, higher energies are being populated. So the energy of the system is going up. So the increase in the kinetic energy of the system can be determined. Alright. Likewise, we can look at the magnetization that is now produced by this promotion of electrons from this spin subband to this spin subband. Now you have more electrons of this kind, because this number of electrons have reversed the spin and come here. So now the magnetization, when you make such a promotion, of electrons from one spin band to another spin band is equal to this area. Now what is this area? This area is GEF delta E. So the magnetization we all know is mu B n alpha minus n beta. Alright, so this is the magnetization. Now I would like to find out this object, n alpha minus n beta. This object is GEF delta E. Now GEF is defined, this is GEF. If this is GE, this is E, this value is defined as GEF. So it's for this unsplit band. So this is for the spin split band. So this is GEF over 2. This is for one spin split band into delta E. This is this particular area. Now this particular area goes here. So the number of these electrons, the minority electrons goes down and the number of majority electrons goes up. So the difference is going to be 2 times this. You reduce this by some number, you increase that by another number, the difference is going to be this. So this number, this magnetization is going to be this number multiplied by mu B. So this is the magnetization that is created. Now when this magnetization is created, because of the promotion of electrons from one spin subband to another spin subband, what's going to happen here is that the Hubbard energy is going to go down because m is now higher. When this m is higher, the Hubbard energy goes down, but it's at the expense of the kinetic energy because the kinetic energy of the system is going up. So we would like to make a compromise, and we would like to see when this can spontaneously happen. It can spontaneously happen when the sum of the kinetic and the Hubbard energy is overall lowered. So now we have calculated the magnetization. We would like to calculate the increase in kinetic energy by virtue of promotion of electrons. Alright, so the increase in the kinetic energy, K, let's call it K. If you look at these spin subbands, the overall kinetic energy of the system after this promotion has taken place is of course going to be the following. It's going to be dE E G E from 0 to EF plus delta E. Correct? This is the total. This is for this spin subband. Alright? Plus, now we would like to find the kinetic energy for this spin subband. This is going to be equal to dE E GE from 0 to EF minus delta E. So this is now the overall kinetic energy of the system. Alright, so let's try to find this out a little bit. And make a few simplifications. I can write this integral K as dE. Remember, this is for this spin subband, so I have a factor of 2 here and I have a factor of 2 here. Because I am defining my density of states GE as the overall density of states. It's the number of electrons of any spin per unit volume, per unit energy. Okay, so I put a factor of 2 here because this is for one spin subband, this is for the other spin subband. So if I look at this integral, dE E GE 1/2 goes from 0 to EF plus 1/2 dE EF plus delta E. So I split the integrals E, GE. Now this integral I write in the following fashion: 1/2 dE E GE from 0 to EF minus 1/2 EF minus delta E to EF dE E GE. Alright, now this is the same as this term. When I add these terms, this term plus this term, I get the energy when the sample is unmagnetized, when there is no delta E. Okay, so I add this term and I add this term to get the kinetic energy when the magnetization is 0. This is the kinetic energy when the sample may be magnetized. So now I have to take into account this term and this term. So I get 1/2. Now this is a small interval. If delta E is really small, I can approximate GE by its average value, which is GEF. So this is GEF. Okay, I can take this out of the integral. I get, this is E squared over 2, so I put a 4 here. I get EF plus delta E squared minus EF squared. Likewise, this would give me minus 1 over 4 GEF, this thing here, EF squared minus EF minus delta E squared. Alright? So I just do the integration. So now this gives me a kinetic energy K in the absence of M. Now I can expand these. For example, if I were to expand this thing, I will get a term delta E squared. I will get 2EF delta E, and I will get, so this expansion is going to be 2 delta E EF plus delta E squared. This term is going to be minus delta E squared plus 2EF delta E. So now I insert all of these values in, and the final result that I get is the following: plus half GEF delta E squared. So this is the energy, the kinetic energy of the band electrons, the itinerant electrons, in the presence of magnetization, when some electrons have been promoted. Alright? Now this is the kinetic energy, and I know that this term represents that the sample is magnetized. Now I know that the magnetization of the sample is given through this formula: delta E equals the magnetization over G at the Fermi level, mu B. So this delta E squared can go in here. I get the kinetic energy in the absence of magnetization plus half GEF. Delta E squared is M squared over G EF squared mu B squared. Now this is the overall kinetic energy of the system. Now let's look at the Hubbard energy. Let's call it U. In the presence of magnetization, that Hubbard energy is written at the top. Now this is the overall energy, by the way. The overall energy. Is it or is it not? No, it's not. Since I'm talking about, so this is per unit volume in fact, because this term is per unit volume. This is the energy, kinetic energy per unit volume. So the overall Hubbard energy per unit volume is, I just divide the expression at the top by capital V, is U over 4 volume of the unit cell, x squared minus m v over mu v squared. Now I would like to add up these energies. That will give me the total energy. This is the Hubbard energy per unit volume, which takes into account correlation between the electrons. This is the kinetic energy. So the overall energy of the system. Now this term and this term both represent the energies in the absence of magnetization. So I can put this term and this term together and I call it E in the absence of magnetization. This is some constant plus m squared m over mu b squared 1 over 2 GE at EF minus this thing here minus U over 4, this is V squared, so I get UV over 4 M over mu V squared. So now let's look at this extra energy term. This is the extra energy term that comes out because of magnetization. And if this term is higher in the presence of magnetization, which means that this term is positive, which means the overall energy is going up, the sample would not like to spontaneously magnetize. However, if this term is negative, the sample would indeed like to magnetize, because that's going to lower the overall energy of the system from its native value. So I would like to look at this term. And if this term is satisfied, I will get a ferromagnet in the Stoner model. So if I look at that term over there, m over mu v squared 1 over 2 GEF at EF minus U V over 4. I would like this thing for ferromagnetism to be negative, which means I would like UV over 4 to be larger than 1 over 2 GEF, which means I would like U into G at EF to over 2 to be greater than 1 over V, the volume of the unit cell. Now this object here is the density of states for the unsplit band divided by 2. So this term I can also write as U density of states for for the majority spins. This must be greater than 1 over V. So if I just look at one spin split band, this is what it is. So this is called the Stoner criterion. So the Stoner criterion tells us that the sample will spontaneously magnetize if this condition is satisfied. If the Coulombic repulsion between the electrons is large, and if the density of states at the Fermi level for a particular band is large. If this product is large, the sample will spontaneously magnetize. Now this both of these terms can be calculated through simulations, through DFT, through density functional theory, and I'll show you some results today. So this is the Stoner criterion, and this tells us that if this condition is satisfied, the sample would like to magnetize spontaneously. And if the sample would like to magnetize spontaneously, it means that if I draw the Fermi level, EF, there will be more spins of one kind and less spins of the other kind. There will be more majority spins and less minority spins. So the sample will become spontaneously magnetized. And this splitting is now not due to an external field, it is due to interactions between the electrons. Sometimes it's dubbed as the exchange interaction. So this is mediated by an exchange interaction. This exchange interaction is modeled through this Hubbard interaction. Okay? So the collective electrons, the itinerant electrons collectively, when they are correlated, they can, if this condition is satisfied, cause the material to spontaneously magnetize itself. And such a material is a ferromagnet. And the three materials, iron, cobalt, and nickel, in the 3D series, they obey this property. Okay? And that's why they are ferromagnetic. So if this condition is not satisfied, then the sample is not ferromagnetic. However, the susceptibility might be different from the polyparamagnetic value. That's possible. Now, how do we calculate? We can also calculate the susceptibility in the presence of interactions between the electrons. G.
Sir, looking at this condition, the right hand side, what would be? We would like this expression to be small, so we would like to be big. So that is why all of the three elements listed are bigger.
No, you have elements to the left and right of this. This just depends on the crystal structure. Different materials, constraint given to us by nature. Different materials will crystallize in their native format. Okay, at certain pressure and temperature. This is just the size of the unit cell. Now, the question is that if this Stoner criterion is met, the element is going to be ferromagnetic. If this is not met, the sample still may have a susceptibility. It's going to be a paramagnet, it may still have a susceptibility, but that might be different from the susceptibility that we write over there for the polyparamagnet. So let's calculate the susceptibility. Now the extra energy, so what we're trying to do is we calculate the susceptibility in the Stoner model, even when this condition is not satisfied. So if this condition is not satisfied, we still have an extra energy term. That extra energy term, delta E, is now given by M over mu B squared 1 over 2 GEF minus U B over 4. This is the extra energy. But now this extra energy can also come in the presence of a magnetic field, because when we talk about susceptibility, we have to find out the change in magnetization by unit field. So we apply an external field now. That external field is also going to change the energy. And how is it going to change the energy? By 2mb. Now what we would like to do, we would like to lower this energy. We like to find out the magnetization that lowers this energy. So what we would like to do is we would like to find this term here. We would like to find what should be the magnetization so that this energy is lowered. This is the condition. And this condition, this is 0. This will give us, if I differentiate, I get M mu B squared 1 over GEF minus UV over 2 minus B. Now, if all of this is equal to 0, I can find out how the magnetization would actually depend upon B. and that's going to give me susceptibility. So J2 is to my mass. So if I do a little bit of algebra over here, I get M equals mu B squared. This B equals mu naught H. H equals M over chi, the susceptibility, and here I have okay. So what so this means that the susceptibility chi is mu naught mu B square, mu naught into mu B square GEF over 1 minus UV GEF over 2. All right. Here I also have a GEF. So since this is the density of set, I don't need this N over here. All right. So now what I have is this term is the poly ferromagnetism divided by 1 minus UV GEF over 2. Now this is not larger than 1 because you don't have a ferromagnet. If you have a ferromagnet, then this term over here, UGEF over 2B, is larger than 1. But we don't have a ferromagnet, so this term is not larger than 1. However, the presence of this term, which is smaller than 1 in the denominator, actually increases the susceptibility over this value. So even though the sample is not ferromagnetic, the presence of interactions between the electrons changes the susceptibility of a paramagnet. So these interactions between electrons have to be incorporated into the theory so that they do match the experimental results. Alright. Now we do some qualitative reasoning and we look at the 3 transition methods in a bit more detail. Any questions after the Stoner model? Because the polysusceptibility did not take into account any interaction between the electrons. So now we have interactions between the electrons which we are modeling through the Hubbard interaction. So that increases the susceptibility of the Stoner model, like all models, has its limitations. For example, it cannot take into account the interactions that are spread over next to nearest neighbors. It does not talk about how these magnetic ions are going to polarize the sea of electrons themselves just by the dipolar interaction. That's why we have the Ricci interaction, which is mediated by conduction electrons. So there are many limitations of the Hubbard model. Sorry? You can build in temperature dependence into the Hubbard model, but the Hubbard model is basically it adds a Coulombic repulsion term which is temperature independent. Okay, so the susceptibility here for a polyparamagnet, if you look at it, is independent of the temperature to first order. It only depends upon the fact that the density of states is dependent on the Fermi level. The Fermi level has a T² dependence on the temperature. So the temperature dependence is really small for those polyparamagnets. Okay? And you should also remember that this GEF is also given by 3/2 MEF. Okay? So polyparamagnets don't have a temperature dependence. Normal paramagnetism does have a temperature dependence. The temperature dependence is only up to second order in temperature. It's very minute. Now what we would like to talk about are iron, cobalt and nickel in some more detail. Okay? Not in a more qualitative and intuitive fashion. So now let's look at the band model. If I have, say, and if I draw the band model, if I have a density of states here and I have an energy here. Now if I look at the 3D series, I have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Before that I have potassium and calcium, right? So this is the fourth period of the periodic table and these are the 3D elements. Yeah. Alright. Now these three elements are ferromagnetic because they satisfy the Stoner criterion. Alright. Now what we would like to see is let's see. So suppose we have copper here. Copper is not ferromagnet. It's a normal diamagnetic material. So the electronic configuration of copper is going to be argon at its core, and we have 4s 3d, and how many electrons? 1 2 3 4 5 6 7 8 9 10 11 electrons in 4s 3d. Okay. Now these 4s and 3d bands, when two copper atoms come close together, these orbitals are going to overlap and will give you bands. You've seen that in the tight binding model. So there is a 3d band and there is a 4s band. Now the 4s band has a large bandwidth. Alright, it has a large bandwidth. This is the bandwidth. Alright, it has a large bandwidth. The 3D band has a small bandwidth. It has a narrow bandwidth. So if I were to schematically plot the 3D bands, this is what the bands are going to look like. So this is the 3D band. This is the 4s band. Now 11 electrons have to go into these bands. Now what I'm trying to do is, one of these channels is the spin up channel, the other is the spin other channel. So I'm trying to split the spins. Now the Fermi level for this system is going to lie somewhere. Okay? The Fermi level lies here. Okay? Suppose it lies here. For copper it does lie somewhere here. I'm going to show you real bands as well. Now the Fermi level lies here. This band has a big bandwidth, the 4s band has a big bandwidth, but it's really small because only 2 electrons can go into this band. So the the density of electrons, the density of states is really small. because it can only fill 2 electrons. But the bandwidth is large, which means T, the hopping parameter, is large. The energy associated with hopping of electron from, in the tight binding model, from one copper atom to another atom is large. So this energy is large. Okay? And since there are fewer electrons, the spacing between the electrons, these are just k levels here inside the energy manifold, is large. Okay? Now this is a tight band. It's a narrow bandwidth band, the 3D band. And the Fermi level happens to lie here. Now what does this mean? This means that all the bands, that both the 3D bands are completely filled because they are below the Fermi level, and the 3s bands are completely filled up to this point. So all the 11 electrons in the 4s 3D bands, they share energy. So the electrons can be shared between the 4s and the 3D band, because in this region of the energy they are shared, the wave functions overlap. So the 4s and the 3D bands are going to hybridize in this region. So now since the Fermi level lies here, all of the both of these bands, in both the spin split subbands, they are going to be filled up to the Fermi level. Now you have the same number of spin up and spin down electrons, and the sample is unmagnetized. So even if there is the Hubbard interaction, and the Hubbard interaction would like to change the position of these bands slightly, nothing is going to change, because you have equal population of spin up and spin down electrons. The sample would not like to magnetize. There is no advantage in shifting the position of these bands through the Hubbard interaction or the exchange interaction. So copper is not a ferromagnet. Now let's look at, say, iron. Now what we would like to do is we would like to follow the rigid band model. The rigid band model says that for different elements inside the series, the band structure does not change appreciably. It's only that the Fermi level changes from element to element. So for copper it lies here, for zinc it might lie here, for iron it might lie here, for cobalt it might lie here. So for the different elements, the rigid band model proposes that the band structure does not appreciably change, only the position of the Fermi level changes inside one period of the periodic table. Okay, so it's a good approximation. We're going to use this approximation now. So now we see that copper is not ferromagnetic because the Fermi level lies in the 4s band. And if any electron that's here, no shifting, no reversal of spins can take place anywhere because everything is jam-packed over here. Everything is completely filled. If an electron here would like to reverse its spin and go here, since the spacing between the k levels is large, the electron will have to increase its kinetic energy by quite a bit. And that's not energetically favorable. So all the action in solid state physics takes place at the Fermi level. Remember that. Now let's look at iron. So I'm using the rigid band model, so I would like to draw the same band picture. GE, E, and I have iron. BCC iron. This is the 4s band. Once again, this is the 3D band. Now this band is split by the Hubbard interaction. Okay. Now the position of the Fermi level for this band, for this BCC iron lies, suppose it lies here. Now the Fermi level intersects with the 3D band. Okay? And these 3D bands are split, which means electrons are transferred from one subband to another subband, because that will lower the overall energy of the system. So what's going to happen if you observe is, if this is a Fermi level, nothing happens to the 4s band. It's not spin split. So the number of electrons spin up and spin down in the 4s band doesn't change. So there is no magnetization due to the 4s electrons. All the magnetization, if any, comes from the 3D electrons. Now if you observe here, this band is filled up to this region. Everything is filled here. This band is, however, filled up to this region. And everything is filled up to here. Now there are more spin up electrons than spin down electrons. Now you observe one thing. The density of states at the EF is large. This is what you observe. This can only happen for the 3D band, because the 3D band has a narrow bandwidth and there are more orbitals in the band. There are more orbitals in the band, so the number of bands per unit volume is large. There are 5 kinds of 3D orbitals. There is only one kind of s orbital. So all of those orbitals have to pack into this narrow region, which means this goes up. So the density of states is large. And if the density of states at the Fermi level is large, then what you expect, the Stoner criterion will be satisfied, because the density of states at the Fermi level is large. You can expect the Stoner criterion to be satisfied. So this really means that the Fermi level intersects with the 3D band. And now what you have is one of the bands lowers its energy, the other band raises its energy because of the Stoner criterion. Now you have more spins of this kind than of this kind. Alright? So this is actually called a weak ferromagnet. Iron is a weak ferromagnet. It's a weak ferromagnet because the majority spin 3D band is not completely filled. It's not completely filled. There's some vacancy over here. It's a weak ferromagnet. Now let's look at nickel. GE, E, the same band structure, the rigid band model. Now the only thing that's going to change is the position of the Fermi level. Now the Fermi level is here. Once again the sample gets magnetized, because there is a higher preponderance of electrons of the majority spin and a fewer number of electrons which are the minority spin. Now what's happened is that the position of the Fermi level is such that it's still intersecting the 3D band, so we expect that the Stoner criterion may be satisfied for this material. And now one of the bands, the majority spin band, is completely filled. This is an example of a strong ferromagnet. It's called a strong ferromagnet. Strong indeed doesn't really mean that the magnetization is large. It does not mean that you have more magnet. It just means that whether the majority spin band is completely filled or not. You have a strong ferromagnet. In fact, you can also calculate or can also determine why is the magnetization per unit cell not an integer of mu b. First, let's do it for this nickel. In nickel, how many electrons do you have in the 4s3d? 10. 10 in total. So you must have a 4s3d configuration and 10 electrons that go into these 4s. So it happens that 9.46 electrons go into 3d and 0.54 electrons go into 4s. This comes out from calculations, from quantum chemistry or from density functional theory. Okay? So you look at the overlap of the wave functions, you can find out the probability densities for the 4s and the 3d, and then you can calculate how much charge is in the 4s and how much charge is in the 3d. So these are numbers that come out from calculations. Now you have 0.54 electrons in the 4s. Nothing is going to happen to the 4s bands. So all those 0.54 electrons are going to remain there. Now you have 9.46 electrons that are going into the 3D bands. One of these bands is completely filled. So how many electrons go into this majority spin band? So it's a d band. So per orbital, so you have 5 kinds of orbitals. Each orbital can carry 1 electron, so you can get 5 electrons. So 5 electrons can go in here. 5 mu b. Okay? This is the magnetization due to this spin sum, minus 5 mu b. Plus or minus, I'll just call it minus 5 mu b. One kind. Each electron has a magnetic moment mu b. So 5 of them will have 5 times mu b. So you left with 4.46 electrons. So those 4.46 electrons have to go here. So you have 4.46 mu b here of the other kind. Okay? So now this band is completely filled. It will not, and this band is at 4.46 mu b. Has 4.46 electrons, in other words. So it's short of 0.54 electrons. This is the number of holes inside this band. Alright? So the number of holes in the band, each one of them will give you a magnetic moment of mu b, because the hole is just an absence of electrons. So the total magnetic moment per iron atom is going to be 0.54 mu b inside nickel. Okay? So this explains why you have non-integer values of mu b. This can only be described with the help of the band model. If you have such a scenario in which, it's quite strange, in which you have a situation like this. Some materials can have this kind of band structure, like chromium oxide. One of the bands is here, the other band is here, and the Fermi level lies in between. Now this band is completely filled, which means the 5 electrons go here. This band is completely unfilled. When this band is completely unfilled, it's going to have an integer number of holes in here. It's going to give you an integer number of Bohr magnetons as the magnetization per formula unit. Such a material is called a half metallic material, in which you have perfect spin polarization. You only have spins of one kind, you don't have spins of the other kind at all. Alright? It's also called a Heusler alloy. a perfect ferromagnet. If you talk in terms of spin polarization. Remember, in this particular case, if the Fermi level intersects with one of the 3D bands, it is actually intersecting with the minority spin band. So if you have conduction in such a material, then that conduction is actually due to the minority spin carriers or due to the holes. So remember, when we talk about, or just keep in mind, transport of electrical transport in magnetic materials is of prime importance. That's why you have the GMR, that's why you have the colossal magnetoresistance, resistance, that's why you have tunneling magnetoresistance, resistance, that's how you have anisotropic magnetoresistance. resistance. So the magnetization of any material is intricately linked with the conduction properties, with the transport properties. So the minority spin carriers play the most important role in conduction studies, because now the band is actually intersecting with the minority band. Here it's intersecting with both, but the density of states for the minority band is larger at the Fermi level. This is larger as compared to this. So the minority spins have the most important role to play in conduction studies. And the last thing, you can have all kinds of nice, beautiful, astounding effects. One last effect that I would like to talk about is how do anti-ferromagnets come about? And I would like to give you one example of manganese oxide. Alright. So in manganese oxide, so the different kinds of models that we've seen, they're either based on the Heisenberg exchange model or the Hubbard model, Hubbard plus tight binding model. In fact, you can prove that the Hubbard plus the tight binding model in certain cases, in certain cases of a particular ratio of T over U square is going to convert, T square over mu is going to convert to the Heisenberg model. So you study models because of this kind. So this kind of interaction is a direct exchange interaction. You can also have manganese oxide, for example, and it's anti-ferromagnetic. So if you look at manganese 2 plus ion, what's the electronic configuration? 3D. What's manganese 2 plus? And for the Moore's rule. Fe5, good. It's isoelectronic with ferric Fe3 plus. So now you have manganese oxide in which you have a manganese atom, 5 d orbitals, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And in each of these orbitals there is one electron. They must be parallel because of Moore's rule. Now let's suppose we have the second manganese atom in which all of them are parallel and these electrons in these two separate manganese atoms, both of them are parallel. Let's suppose this is the case. In between we have an oxygen anion. So this is manganese ion. It's an ionic crystal. Okay. And you have an oxygen anion in between, and you have the 2 electrons in a p orbital, and they must be anti-aligned because of the Pauli exclusion principle. Now when you know that if the wave function of electron is spread out over a larger area, its energy goes down. If you consider the potential in a well problem, if the width of the well is large, then the energies go down because they go down as 1 over L squared for a one-dimensional well. So the electron from an oxygen anion may hop from this anion to the manganese ions, and a covalent bond can be formed. This is the hopping integral that we talked about. Now if you look at these two electrons, they are anti-aligned because they're in the same orbital. If you have this configuration, you look at this electron cannot go here because the spins are parallel. And any hopping preserves the spin. If you have spin preserving hoppings, then this electron cannot go here. This electron, however, can go here and it can go here. So only one of the two electrons can actually hop on to a manganese ion. Alright? Now let's consider the opposite configuration. We have two manganese ions, 1, 2, 3, 4, 5. Once again we have the same parallel alignment, and here we assume that you will have parallel inside the manganese, but you assume that this is anti-parallel with respect to this. Now you have the oxygen anion in between, which is the bridge between the two manganese ions, two electrons. Now this electron can make this transition, and this electron can make this hopping. So now each of the two electrons can minimize its energy. So out of these two configurations, which is the lowest energy configuration, this one. So this configuration actually necessitates that two neighboring manganese ions have their spins pointing in opposite directions. So this is how anti-ferromagnetism is energetically favorable for manganese ion oxide. This is why this insulating oxide is anti-ferromagnetic, and there is no direct exchange interaction between these electrons, between these ions. So this kind of interaction is called a superexchange interaction. It's an example of a superexchange interaction. You can also have another interaction, with, for example, the Ricci interaction, RKKY interaction. It is the Ruderman, Koshaya, Kittel, Yoshida interaction. In this interaction, you have a magnetic ion, for example, a 4F ion, gadolinium, terbium, dysprosium, the 4F ion, and a sea of electrons. And the ion polarizes the electrons, right? And then the wave function of the electron takes an oscillatory character. So you have, at this location you have spins of one kind, at all the crests you have spins of one kind. So if this is the interaction between two magnetic ions, this is the distance, then those magnetic ions would like to ferromagnetically order. So this kind of interaction is mediated by the conduction electrons, and it's called an indirect exchange interaction. The Ricci interaction is one example of this, so we don't have time to go into this. So magnetism is actually a really rich field. So last I would like to show you 4 or 5 slides which just going to show real band materials, band structures. And that will inshallah conclude our course. Just for Numan, I would like to say that they generally say when you finish something, what do you say? Shadam az zindagi khish ke karya karna. You know what that means? I'm happy with my life that I've done the work that I was supposed to do. That's why they also say, Gumam avar ke vapaya receive kare mua, hazar badaye na khudda darage takas. Don't think. ये ना सोचो कि जो शराब पिलाने वाला है साकी है उसका काम खत्म हो गया है, अपने काम तक पहुंच गया है। बहुत सी अभी उस वाइन यार्ड्स के अंदर ऐसी मैं अभी मौजूद है जो भी निकली भी नहीं है, तो वो काम आपने करना है। Alright, so here is the graph of, so this solid graph shows you the density of states at the Fermi level, G, and it's G here, for different elements inside the periodic table. Alright, the solid graph. This is the density of states at the Fermi level, GEF, for one of the spin subbands. And the dashed curve gives you 1 over U. So you want G to be larger than 1 over U. Or you want G, U to be larger than 1. So you want G to be larger than 1 over U. That's the Stoner criterion. So this dashed curve represents 1 over U. I is U here in my notation. So if you observe, iron, cobalt and nickel have their heads sticking out of this graph. So Stoner criterion is satisfied for these elements. Scandium is really close. So if scandium had a little bit higher density of states, it might become ferromagnetic. Palladium is exceptionally good. Palladium and platinum, these are on the verge of becoming ferromagnetic. These are paramagnetic materials on the verge of becoming ferromagnetic because the properties of these materials, the density of states is just at the edge. Yttrium is also good, but scandium is actually quite good. It's close to becoming a ferromagnet. And remember, iron can crystallize in different forms. BCC, FCC, etc. You can have different kinds of phases for these materials. Some of them can be ferromagnetic, some of them can be paramagnetic, right? So this is the Stoner criterion. Now this is what I actually showed you. I talked about the strong ferromagnet. One of the spin subbands is completely filled. At the top I have a weak ferromagnet. There is still a ferromagnet, but the majority spin band is not completely filled. Both of these will give you non-integer values of mu b for formula unit. This is a tight binding rough diagram of its cartoonic representation of, you have a band structure which is now represented in a more realistic fashion. This curvy band structure. Copper, the Fermi level is above the 3D band, it lies in the 4s band. Zinc is right at the top because everything is completely filled. The 4s and the 3D are completely filled for zinc. So then you have nickel, cobalt, iron, manganese. Okay? Now let's look at manganese. Why is manganese ferromagnetic? Now these are real band diagrams acquired through a simulation performed in DFT by some researcher. So you have scandium, titanium, vanadium, chromium, manganese. If you observe in all of these elements, the Fermi level intersects, has a small value, the density of states has a small value at the Fermi level. However, in the case of nickel, cobalt and iron, the density of states at the Fermi level is really large. So the Stoner criterion is expected to be manifest in these three elements over there. Okay? For copper and zinc, of course, the Fermi level lies in an uninteresting plain 4s region. So you don't expect ferromagnetism in these materials. So this is in the paramagnetic state, but in the, and you can also draw diagrams in the ferromagnetic state. So you draw the spin split bands here. You know, iron, cobalt, nickel. So this is what you would observe. Okay. If you look at nickel, nickel is a strong ferromagnet because this band is completely filled. What about cobalt? Cobalt is also a strong ferromagnet. But iron isn't. Look at iron BCC. Iron FCC. Iron FCC with a certain unit cell, 0.358 nanometers at certain pressure, temperature, etc. is not ferromagnetic. But the same iron FCC structure under different conditions with a different unit cell. So depending on the unit cell size, you can have paramagnetism or ferromagnetism, alright? So these are just numerical, these are just values that were three parameters that were put into the simulation for A, the size of the unit cell. And if you talk about the moments in metallic ferromagnets, you have nickel, these are the Curie points. M naught gives you the number of newbies per unit cell. So for nickel, it's 0.554 as I mentioned, it's about 0.59, probably 0.6. So this is NEF, so this is ratiometric. If nickel has a magnetic moment has a saturation of 1.0, this weak itinerant ferromagnet, the zirconium zinc compound has 1.8, chromium dioxide, which is a half metallic material, is 2.4. And notice that for the half metal, you have an integer number of Bohr magnetrons, 2.0. Alright, so I've uploaded the last homework. So please submit the homework in time. This is my usual request. Inshallah, I'll see you on your final exam. I may not see you on your final exam, but you will see me virtually during the final exam. Okay, good. Oh, thank you. Thank you.
We had a small class. Most of the time were absent.